Imagine a fully loaded production line, humming along perfectly, and then, instantly, it all grinds to a jarring halt. The screen on your variable frequency drive flashes a fault code. Resetting it might get the line moving for a few minutes, but it doesn't solve the underlying issue. We are going to break down the big three VFD faults: voltage trips, overcurrent, and electromagnetic interference, so you can trace them to their source. Before opening any panels, you need 4 things in place: strict lockout-tagout safety protocols, a digital multimeter, your specific VFD manual, and the motor's physical nameplate. Endlessly hitting the reset button risks permanent damage to the drive's internal components. Identifying the specific source of a trip is the only way to restore the process and prevent the fault from recurring an hour later. Step 1 is looking at the VFD display. A voltage trip usually falls into one of 2 categories: undervoltage or overvoltage. They require completely different diagnostic paths. If the screen reads undervoltage, the drive isn't getting enough power to operate. Take your multimeter and check the incoming AC supply lines. Look for a blown input fuse, a dropped phase, or a severe line voltage dip. If the screen reads overvoltage, the initial assumption is often that the power company sent a spike down the line. Most of the time, the incoming supply is perfectly fine. The excess voltage is actually being generated by the motor itself. When you slam the brakes on a heavy load, inertia overhauls the motor, pushing energy backward and spiking the DC bus voltage. To fix this, extend the deceleration time in your software. A slower coast down shrinks the reverse energy flow, keeping the voltage completely stable. If your process absolutely requires a fast, aggressive stop, tweaking the software isn't an option. You will need to install a dynamic braking resistor. This hardware add-on bleeds off the excess regenerative energy as heat. By identifying whether the energy is missing from the incoming supply side or surging backward from the load side, you know exactly what to measure and which adjustment to make. Let's move to the second major fault: overcurrent. This simply means the motor is demanding more amperage than the drive's hardware can safely supply. Because an overcurrent trip can be triggered by physical friction just as easily as bad data, our first step is locking out the power completely. We need to take the electrical system out of the equation. Go to the motor and mechanically uncouple the load. Spin the shaft by hand. You are feeling for seized bearings or mechanical binding. Check the VFD heatsink fins as well to ensure they aren't blocked by dust. If the shaft spins freely, the issue is likely electrical. While it could be a short in the motor windings or damaged cable insulation, you should first check the VFD's configuration to see if it's pushing the motor beyond its rated limits. This comparison shows exactly what you need to check next. You must verify that the voltage, full load amps, and RPM entered into the drive's programming match the physical motor nameplate perfectly. If the data matches, the drive might just be pushing the motor too hard from a dead stop. Try extending the acceleration time parameter to ease the motor up to speed. You can also lower the startup boost setting, which reduces the initial surge of voltage. By ruling out physical friction before you even touch the keypad, you isolate the problem to the electrical side of the system, preventing you from replacing expensive mechanical components that are still functional. Now for the third category: ghost faults. These are the communication losses, analog signal drops, and intermittent errors that happen at random and leave no mechanical or programming trace. The invisible culprit here is electromagnetic interference, or EMI. VFDs create very rapid, high-voltage switching transitions. If the installation isn't secure, that high-frequency noise bleeds right into your low-voltage control signals. The first defense is distance. Ensure your heavy power cables and your sensitive control cables are separated by at least 8 inches. They should never share the same conduit. Even with proper distance, you still rely on shielded cables, but a common mistake ruins that protection: stripping the shield back and twisting it into a long pigtail to reach a ground lug. This shows why it matters. On the left, a twisted pigtail acts like an antenna, radiating high-frequency noise into nearby data cables. On the right, the exposed shield is secured with a 360-degree conductive clamp to an unpainted grounding plate, creating a continuous Faraday cage. Maintaining electrical hygiene and grounding discipline contains switching noise at the source. This prevents intermittent signals from disrupting the logic of your control system. With the parameters verified and the grounding secured, close the panel, restore power, and issue the start command. The motor smoothly comes up to full operational speed, drawing perfectly balanced current. We diagnose these issues using a strict 3-pronged framework: separating voltage supply issues from load regeneration, isolating mechanical binds from electrical configurations, and controlling EMI through proper cable routing and grounding. Now that the system is stable, you can consult your manufacturer's documentation to optimize your V per hertz curves and sleep modes for long-term energy savings. Systematic isolation takes the guesswork out of troubleshooting. It shifts daily operations from reacting to sudden maintenance headaches to maintaining a predictable, efficient process.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.